In this video, we'll give a brief introduction to ketones and aldehydes, two of the more important oxygen-containing functional groups that we'll encounter in our voyage through these functional groups. Our learning goals will include learning about the physical characteristics of the carbonyl bond, the carbon-oxygen double bond, and identifying aldehydes and ketones and being able to recognize them from one another. So let's learn about the carbonyl bond. Okay, this is basically the carbon-oxygen double bond that can appear in lots of different molecules, and in fact it's quite ubiquitous. We will find that the carbonyl bond appears in a lot of different settings. It's in several functional groups, and it has many important properties. I think one of the most important is that it has very strong charge separation. It is stabilized by a resonance. So for example, we could have a pair of electrons that jump up from the double bond between carbon and oxygen up to the oxygen to form a negative charge up there as one of its resonance structures. Notice that this particular resonance structure also leaves a positive charge on the carbon, and this is very revealing because due to the polarity of the bond, we find that the carbonyl bond does have an electron-rich center around the oxygen and an electron-deficient center around the carbon, and this is one of the things that makes it such a versatile piece of any carbon framework molecule. It's a very strong bond, 745 kilojoules per mole, so it's very sturdy. These are very durable sorts of pieces of molecules. It can act as both a nucleophile at the oxygen end and as an electrophile at the carbon end, and this is in part due to this charge separation that occurs in the bond. So a carbonyl bond might be more realistically drawn something like this, where we've got a partial positive charge on the carbon, a partial negative charge on the oxygen. The carbon end is the electrophilic part because it's electron poor, while the oxygen end is the nucleophilic part. So with a piece of your compound that can act as both an electrophile and a nucleophile, you really have a versatile piece that can now participate in a lot of intermolecular interactions as well as chemical reactions later on down the road. So what are some of the functional groups that contain carbonyl atom? Well, first, and one that we'll talk about in this video, is the aldehydes, also ketones. There are also carboxylic acids, esters, amides, acyl chlorides, and acid anhydrides. All of these are primary functional groups that contain the carbonyl bond, and what I've tried to do in this is to circle the part of that basically identifies the group. So in an aldehyde, what identifies the aldehyde is that it has a hydrogen attached to the carbonyl. For the ketone, it's just having the carbonyl in the midst of a carbon chain. For the carboxylic acid is having OH attached to the carbonyl. For an ester, having another oxygen, which then connects to another alkyl group, is the identifying piece. Amides have an NH2 attached to the carbonyl, and acyl chlorides a chlorine. An acid anhydride is basically a fusion of two carbonyl groups with a bridging oxygen. Now these all have distinctive signatures when we look at their MEP surfaces. But one of the things I want you to notice from this is that the carbonyl group is very similar in each of them. It is a big red dome. So if you see that big red dome in an MEP surface, you can be fairly assured that you have a carbonyl bond as part of that molecule. You'll also notice that each of these molecules have, to varying degrees, positive centers. In the case of the aldehyde, it's everything that's sort of opposite the carbonyl bond. In the case of the ketone, it is, of course, the carbon that's opposite the carbonyl bond. But in the carboxylic acid, the positive center is actually centered on the hydrogen that's attached to the carbon, is attached to the oxygen on the carbonyl. So we have a variety of different things. The fact that there's interesting different charge distributions in these molecules makes each of these functional groups very distinctive and gives it different physical and chemical properties. So let's talk about aldehydes. Okay, remember, this is one where we have a terminal hydrogen bonded directly to the carbonyl bond. This is sometimes abbreviated as CHO, so you may see some, if you have a structural formula written down, you may see CH3, CH2, CHO. When you see CHO, it's trying to imply that you have an aldehyde group there at the end. The names for aldehydes typically end in al, or they could end in aldehyde. So benzaldehyde is an aldehyde. They're more reactive than ketones anyway because carbonyl group is not blocked. The hydrogen doesn't really get in the way of anything that needs to come in and react with the carbonyl, so it's very easy to oxidize a carbonyl bond in this case. It occurs in lots of natural products, including linear monosaccharides. Monosaccharide is basically a natural sugar, and it has a noticeable scent. So I've drawn glucose up here, which is a monosaccharide, and you can see the aldehyde is at the top of this structure as it's drawn. Now, glucose also can form a cyclization reaction, and so the kind of glucose that you typically find in food matter is the cyclic form. But the linear form is an aldehyde. The cyclic form is a polyalcohol. All right, let's look at ketones. Now, in the case of ketones, instead of hydrogen attached to the carbonyl group, each side of the carbonyl group has an alkyl group attached. So I've labeled those R1 and R2. The names of ketones usually end in ONE, so that's another way you can identify them. They have bulkier side groups, so that makes them less reactive. They're more difficult than aldehydes to oxidize because of that blockage. Basically, other species can't access the carbon that's attached to that's part of the carbonyl bond. That polarity of the carbonyl bond, though, does lead to strong intermolecular forces. So these compounds tend to have higher melting and boiling points. They stick together more readily. One that you may have come into contact with is acetone, which is a particularly good polar solvent. It's used in fingernail polish remover, for example. It's also used in a lot of the organic labs. So if you have ever taken an organic chemistry lab, you almost certainly have come into contact with acetone. Now, ketones also are a key ingredient of pheromones and hormones. Okay, pheromone is a chemical that's used by animals basically to communicate. So ants leave pheromones along their trail so that other ants can follow them and find out where the food is. They also use pheromones as a sexual attractant and for other purposes, but it's basically a universal way that animals can communicate with one another by using these chemicals. Okay, some of these pheromones are ketones. So 2-heptanone, for example, is used by bees. That's when they want to signal an alarm. And this very long chain ketone is used as a cockroach sex pheromone. So you probably don't want to wear this one very much on your clothes or you'll be attractive to cockroaches. Ketones can also serve as sex hormones in humans, so you may be familiar with things like testosterone and progesterone. And I'll point out that in testosterone, there's a ketone group at the lower left. In progesterone, there are 2 ketone groups, so it's a diketone. So ketones play a fairly important role biochemically in a lot of biological chemistry. And you'll come into contact with many different ketones as you learn more about chemistry.